Most people think neural networks are only for classification. But what if a model could learn to compress data, remove noise from images, and reconstruct information almost like magic? In this video, I'm going to show you a complete hands-on project on autoencoders using PyTorch, where we'll build neural networks that learn efficient representations of data completely on their own. We'll start from the fundamentals of encoding and decoding, understand how dimension reduction works, and then move into image reconstruction. The really interesting part here is we'll build a denoising autoencoder capable of cleaning noisy handwritten digit images. This is the exact project that I led here, and throughout the video, I'll explain not just the code but the intuition behind every step. Architecture design, latent space learning, reconstruction laws, training process, and why autoencoders became the foundation for many modern AI systems. So if you want to understand deep learning beyond just classification models, this video is going to be extremely valuable for you. Let us begin. Hello and welcome to this session on autoencoders. Now, autoencoders is a very important architecture in deep learning, and our use of autoencoder throughout this section really falls a lot more under unsupervised learning rather than a supervised learning. Recall that previously throughout the ANN section, recurrent neural network and convolutional neural networks, we were dealing with historical data that were already labeled for us. We already knew what, for instance, the image label was, whether it was a dog or cat, or whether it was whether it was a cancerous benign tumor. So when we are dealing with autoencoders, our use case for them really falls under unsupervised learning. So I really want to review what applications we are going to be using autoencoders for and why it is labeled as unsupervised learning instead of supervised learning. So we are going to be using autoencoders for two main things. One is dimensional reduction, which is pretty much what all autoencoders do to some degree. And then we'll see how we can use this dimensional reduction to actually remove the noise from images. So during the training of certain models, we actually sometimes get access to historical data with correct labels. However, during the actual use of the model, we won't be able to use our previous evaluation matrix, and that will make a lot more sense when we actually see how we construct these models and how we actually use them in a real world situation. So recall that unsupervised learning means we don't have those correct labels to compare our results to. And I should mention that our use case for autoencoders are actually sometimes called semi-supervised. So it is not completely unsupervised, but it is definitely not completely supervised either. So sometimes people like to call this as semi-supervised. Now, the reason they use this term semi-supervised is because while we are actually training the autoencoders, we do take advantage of having sometimes historical labels. However, when we are actually using this autoencoder, we don't really have a situation where we can produce some sort of nice classification report and some sort of maybe root mean square error or accuracy. And that will make a lot more sense when we see the use cases of dimension reduction or noise removal. So to fully understand this, we have to first understand what autoencoder is and how it actually works. Autoencoders is actually a very simple neural network and will feel very similar to the multi-layer perceptron models that we built during the artificial neural network section. And the main idea is that an autoencoder is designed to simply reproduce its input at the output layer. So that means the key difference between an autoencoder and the typical MLP network is that the number of neurons is equal to the number of neurons at input is equal to the number of neurons at output. Typically in our use case, we have been either having the output be equal to certain number of classes that we are classifying for, or equal to one neuron if you are dealing with the continuous output. However, in kind of a strange case here for the autoencoder. The number of input neurons is exactly equal to the number of output neuron. So let us explore what this actually looks like and why would we would want to be able to build a network this way. So here we can see an example autoencoder. Notice the shape here. We start with 5 neurons and then slowly we are reducing down to a certain specified number of neuron throughout the hidden layer. So you go to maybe it's 5 to 3 to 2 1. And the main idea here is right in the middle of your autoencoder, you are going to reduce to some desired amount of neuron, essentially trying to capture what information is important. And in the second half of the autoencoder, essentially the decoding part, you expand this back out to equal to the same number of neurons that you started with. So we go from 5 to 3 to 1 and then back to 3 to 5 again. So we start at 5 and we end up at 5. That is the gist of the uh, autoencoder, and very important point that you have to take away home. Now let us walk through the layers and see the basic idea of the autoencoder. And to simplify this further, let us imagine that we have this very a simple single layered architecture. So you go to 5 to 2 to 5 back again. And the idea here is that in order to produce the same output at the final layer, that the hidden layer, or specifically the internal multiple hidden layers for a real autoencoder, for example, those hidden layers must actually learn what features are important. And this kind of extreme example basically shows you that in order for this input to be reproduced as output, those two neurons in the hidden layer, they are going to have to learn which inputs are actually important in order to reproduce the output. So they are reducing the amount of dimensions from 5 to 2. So again, we see here that we have a dimension of 5 reduced to a dimension of 2 and then expanded back to the original 5. Notice my use of the word dimensions. I'm not saying the word features here. Okay. Again, the feed-forward network is trained to produce its input at the output layer. This is what all autoencoder is. We have some input that gets reduced to a hidden layer in the middle and then expanded back to the original size in the output. This is the architecture of the autoencoder. Now, output size here again same as the input size, and that hidden representation attempts to maintain the important input information before being decoded or expanded back out. And then later on, we'll see how we can actually take the advantage of that hidden layer to extract meaningful insight. So when we do things like dimension reduction, we'll be actually be able to train a full autoencoder and then split it in half and directly extract results from the middle hidden layer. But the full autoencoder is actually inputs shrunken down to hidden and then expanded back out to output. So this idea is actually extremely similar to principal component analysis in statistical machine learning models. We are trying to reduce, classical machine learning models. Here we are trying to reduce the dimension reduction we are trying to reduce the dimensions into a fewer principal component. And keep in mind that we can explore stacked autoencoders with more hidden layers, and we'll actually be doing this ourselves throughout the Jupyter notebook or Google Colab shortly. Now, a really important note here: a lot of uh, learners, they get confused by this term reduction in dimensionality. Keep in mind that those hidden layers, they are not simply subselection of only certain feature. So it's not like that you start off with 10 feature and then you choose 8 of those 10 feature to continue on with. What you are actually doing here is you are calculating the combination of the original feature to represent the original dimension in a reduced dimensional space. So again, you're not sub-selecting feature, you are actually taking a little bit of all the features, some percent depending on the way the autoencoder is trained. So for example, you may take my maybe 5% of feature one, maybe 10% of feature two, and etc. And you decide how important is each feature as you slowly reduce this dimension down. And then that hopefully that hidden layer in the middle is going to learn which features are the most important and how to organize them in a way to reduce the dimensionality. And then again, to check if it is working or not, we decode or expand this bag to the output layer. So again, we are not sub-selecting only certain features. So what does it look like in practice? Well, later on, we'll see that we are going to explore how we can actually use an autoencoder and split it into two parts and a encoder and a decoder to perform dimension reduction. So we'll be able to actually take a three-dimensional data set and then reduce it down to either two or even one dimension. So notice here that we have two cluster and we are able to map them to a lower dimensional space and still maintain this separation. So in this particular use case of going down from 3 to 2, that may not look actually very useful to you. However, you can imagine that if you are dealing with a data set that are much larger than just three feature, so if you have a data set maybe about of maybe 30 feature or 40 feature, something very large, you cannot just visualize those 30 feature in three-dimensional space because we are living in a 3D world. So to visualize them or to see the get some visual idea of those feature, what we'll do is we will reduce the dimension using this technique and put it back to maybe 3 dimension or 4 dimension, then just plot it out, right? So as we reduce this down dimensional, right, dimensionality wise, you can imagine that if you are start off with a very high dimension data set that was too highly dimensional to visualize, we could reduce this down to 3D to or 2D and then visualize the classes and see just how separable our data set is. And then later on, we'll see how we can apply this to just reveal hidden insights from our data. Again, the main idea behind an autoencoder is the center hidden layer reduce the dimensionality to learn the most important combinations of original feature. And we are going to see two applications of the autoencoder. They both use an autoencoder here, but they use them in very different ways, which is why this is such an interesting network architecture, because even though you have the same network architecture of inputs being reduced and then matching the output size, you can use them in a variety of tasks. So again, we'll be exploring two use cases. One is the more obvious one, that is the use case of dimension reduction, where you essentially after training an autoencoder split it in half and just extract the hidden layer output. And then the second use case is a really interesting one for the noise removal. For the noise removal, you will actually have that hidden layer essentially learn how to filter out noise when reproducing the output. So both of these uh, use autoencoder, but they use them in a different manner. They are super interesting problem sets. So what we are going to do is we are going to first explore the first one, that is autoencoders for the dimension reduction, and then we'll talk about the noise removal. Let us talk about dimension reduction before we go to the coding part. So we can use an autoencoder for dimension reduction by separating out the autoencoders into two parts, the encoder and the decoder. Now, here we have the full autoencoder. Recall the autoencoder, the main idea here is that we have the same number of input as we do output. And then inside of the autoencoder, we do a dimension reduction and then expand this back out to the original dimensions. So what we end up doing is we separate this out into two parts, an encoder and a decoder, where the idea of the encoder is to take something that is highly dimensional and then encode it into a lower dimensional space. And basically the decoder's job is to expand back out that low dimensionality in order to make sure that hidden layer in the middle of the autoencoder is actually learning correctly what features are important, because if it is not able to learn correctly what combination of feature is important, then you're going to have a really poor output. That is the job of the decoder. So what we do is we train this all together until the hidden layer becomes really good at extracting useful information, and then a decoder can expand that back out. Once we have trained the full autoencoder, then just grab the encoder section. And now we have something that successfully reduce the dimensionality. So we train them together, but when we actually want to use them, we will only grab the encoder part. So this encoder can now successfully reduce the dimensionality of the original data by taking the combination of the original feature. And well, you may be asking what use case does this have. Again, I've already I've already explained this, but dimension reduction, and I'll repeat myself, that dimension reduction has a wide variety of use cases. It can be used for things like compressing your data set, visualizing data in lower dimensions, and most importantly, revealing hidden relationships that are not basically clearly seen unless you plot them out obviously, right? So when you're dealing with feature data that goes beyond 3 dimension, then it becomes difficult to actually visualize this and understand the relationship, especially if you're performing something like a classification task. So it may be quite useful to understand just how separated are these classes. And if you're able to visualize this either in 3D or 2D, you may be able to get an understanding of just how separable these classes are. So, for example, here we have an example of a dimension reduction. We are starting from 3 dimensions again, and we can see we have 2 clusters that are highly separable, and we are able to actually visualize 3 dimension. But you can imagine that this could have been 11 dimension, or maybe 41 dimension, or maybe 100 dimension, where there is no way to visualize the classes themselves. So in that case, you would reduce the dimension to maybe 2 dimension or 3 dimension, and then just plot them out. Now, let us actually code this out exact problem set. And for that, I'll hop back to the Google Colab. So here I am in my Google Colab. Let us start with importing some of the important libraries. So I'll say import NumPy as NP. I'll import pandas. I'll import matplotlib. I'll import Seaborn as SNS. Before moving on, again in Google Colab, it is highly recommended that you should turn off the AI assistance. That is good for you, especially if you are in your learning phase. So go to tools here. In tools, you should find the settings. In settings, you are looking for AI assistance, and just uncheck this one, right? So just uncheck this and you're good to go. All right, it is highly recommended that you do that. Now I'll import from scikit-learn a data set. All right, so I'll say make blobs, and I'll say number of samples as, let us say, 300. So it creates a synthetic data set using the macblobs function. So it is going to contain 300 sample with 2 features, and is clustered around 2 centers, and standard deviation of the cluster is, let us say, 1. I'll say some random state as well, 101. Assign this to some variable. I'll call this as maybe I'll call the data, right? And so if you check your data here, is going to be a tuple where first one is the array. You can say it's a tuple. You can check this out if you are not sure. You can say type in data. It's a tuple, right? So inside this tuple, the first thing or the first component is your array, that is your feature. And the next one is y, right? That is the label. So I'm having x for the feature and y for the label. All right. And now you can just check y here again if you want to. You can see there are two clusters here. So centers are two, thereby I'm having 0 and 1. All right. And x again, you can check this if you want to get the shape. You'll see that it is having a shape of 300, that is the number of samples, and 2 being the feature. So this x1 and x2, and that y was basically the y, right? It was the label. Now, I'm going to generate a 1D array of normal noise from a normal distribution. So I'll say np dot random dot seed and pass in maybe 101. I'll say z noise equal to np dot random dot normal size equal to length x. So here we have created this z noise here, and if you check z noise, you can see it's an array again. Now what I'm going to do is I'm going to pass this as a series, and you'll understand why I've done that. But let me for now, so basically I'm creating the data here, and I'll be using the same data so that we don't have to use an external data, right? So this is my z noise. Right, I've converted the array of noise into a panda series, which is a one-dimensional labeled array capable of holding any data type. Now, I'll do one more thing. I'll say pd dot data frame, pass in x here, and assign this to, let us say, feature. Then I'll say pd dot concat feature noise, and x is equal to 1. And if you run that, you have this. Now this is feature as this. I'll do one more thing, that I'll take the, and this I'll say as x1, x2, x3. Right, so I'll say feature dot head as this. Just a second, this has to be equal to. All right, so we have basically created this data frame. Now, what is the point of this? If you just try to plot this out, you will see that plt dot scatter between any two things or any two feature x1 comma x2. All right, and if you just take the color equal to the y label that you had created. So if you run that, you can see this is the, two x1 and x2 that we had previously. All right, great. Now, I'll also try to show you the 3D plot. Now, 3D plot per se, it is not actually very important for us to, we don't have that much of use case of 3D plot, but you can use this and you'll say MPL toolkits dot mplot 3D import access 3D. I'll say plt.figure as this and figure equal to this. All right. Then I'll say x equal to figure dot add subplot. And I'm just saying that number of rows is 1, 1, 1. All right. And then projection. Okay. Then I'll say x dot scatter, pass in feature x1 and x2 feature. So I'm trying to plot everything here, right? In 3 dimension, and color is equal to y as well. All right. So you can see this is the thing that I'm getting. Okay. Now let us get the next thing up, that is encoder and decoder. Right. First one is import torch, torch.nn snn, torch.optim, optimizer as optim. I'll also import from pre-processing. I have to import min-max scalar, skleon dot pre-processing import min-max scalar dot. All right. Again, Torch imports the Torch library, which is built for training. Sorry, it is used for building and training neural network in Python. And then we have the NN module that provides classes and functions for constructing the neural network. Then we have Optim module, which provides the optimization algorithm for training neural network. Next is we have to define the encoder. So I'll say class encoder is going to inherit everything from the nn.module class, the base class for all the neural network modules in PyTorch. And then inside that, we'll have the constructor method, that is def underscore underscore init underscore underscore self. And then I'll have super encoders. It calls a constructor of the parent class self.encoder layer, that is nn.layer 3 by 2. So I'll say encoder comma self dot underscore underscore init underscore underscore self dot encoder layer equal to nn dot linear and 3 by 2. I'll say def forward self comma x and return torch dot relu self dot encoder layer x. All right. Uh, so we have gotten this forward pass here of the encoder. So the input x is passed through the linear layer, and a relu activation function is applied to the output. Then we have to define the decoder. Sorry, this is class decoder. Again, it is going to inherit everything from the nn.module. And I'll say def underscore underscore init underscore underscore self, and is going to have super decoder comma self dot underscore underscore init underscore underscore, and then I'll say self dot decoder layer equal to nn dot linear 2 by 3. Then you'll have the forward pass, self comma x here, and it's going to return torch dot relu and self dot decoder layer x. Okay, now we so we have gotten the decoder class here. Just to explain this, it defines a decoder class similar to encoder. Self dot decoder layer. Then you have the nn dot linear 2 by 3 defines a linear layer with a 2 input feature and 3 output feature. Then we have the forward pass of the decoder applying a ReLU function after passing the x through the linear layer. And then we'll have to define once you have the autoencoder. Sorry, we have the encoder and decoder. Then we'll define autoencoder here. Autoencoder nn dot module. Let's say def underscore init underscore self. Then I'll say super autoencoder comma self dot underscore init underscore. Here is this. I'll say self dot encoder equal to encoder self dot decoder equal to decoder. Okay. Then lastly, I'll also have the forward pass as the encoded equal to self dot encoder x and decoded equal to self decoder. And we obviously in decoder we have to pass in the encoded part, right? And then I'll return the decoded. All right. So again, what you have done in this autoencoder class is we have combined autoencoder and decoder. Encoder, it creates an instance of the encoder class. This creates an instance of the decoder class. Then this defines the forward pass of the autoencoder. The input x is passed through the encoder to get the encoded representation, and then through the decoder to construct, or should I say, to reconstruct the original input. Now what I'm going to do is I'm going to instantiate the model. Hopefully everything is fine that we have done. So I'll say autoencoder, and then we have autoencoder here. There we go. Next is to define the loss function. So I'll say criterion equal to nn dot msc loss and optimizer is equal to optimizer dot stochastic gradient descent. And then I'm taking that instance that is autoencoder and I'm calling the parameters from this. Learning rate equal to 1.5. All right, so it defines the autoencoder as a stochastic gradient descent that is responsible for updating the model's parameter to minimize the to minimize the loss. And then autoencoders dot parameter, it passes the modus parameter to the optimizer. Learning rate being 1.5 is the controls how much to change the model in response to the estimated error each time the model weights are updated. So this is the optimizer here. All right, then I'll scale the data. So I'll say scalar equal to min max scalar, and then scaled data equal to scalar dot fit underscore transform is fit, right? Then I'll say scaled data tensor equal to torch.tensor as scaled data and d type equal to float 32. So I'm mentioning the data type here. Sorry, this torch.float 32. All right. So again, it converts this one actually torch.tensor. It converts the scale data into a PyTorch tensor with a data type of float 32. Tensors are the core data structure in PyTorch, similar to the arrays in NumPy, but with additional functionality for GPU acceleration. Then I'm going to train the I'll train the autoencoder here. And for that, I'll first have to define the epochs. I'll define that as at least 15. And I'll say for every epoch in range epochs, I'll say optimizer dot zero grad. That clears the gradient of all optimized autoencoder here. And uh, then gradients from previous step are accumulated by default, so they need to be resetted at the start of each training step. Then I'll say outputs equal to autoencoder and pass in the scaled data tensor. So it passes the scale data tensor through the autoencoder to get the reconstructed output. And then we have the losses. So I'll say loss equal to criterion, pass in the outputs and scale data tensor. Then loss dot backward that computes the gradient of the losses with respect to the model parameter. This step is crucial for the optimizer to know how to adjust the weights. And lastly, you'll say optimizer dot step. So this updates the model parameter based on the computed gradient to minimize the losses. But let us now print this. All right, so I'll print the current epoch number. Okay, then loss dot item. All right, so that's that extract is the external scalar value from the loss tensor. Then I'll say encoded 2 dimension equal to autoencoder dot encoder here, then say scaled data tensor dot d dash dot numpy here. All right, so it passes the scale data through the encoder part of the autoencoder to obtain the 2D encoded representation. Then dot detach method is used to create a tensor that is no longer connected to the computational graph, meaning it won't track gradients. Then numpy converts the tensor to a numpy array to easy manipulation and visualization. I'll say plt dot scatter. Let's say encoded 2 dimension as 0, then encoded 2 dimension as c equal to y. I'll say plt dot show. Let us run this. Hopefully I'll not get any error. Let us run this. All right, I have gotten the error, and that is in here. So yeah, after detach, you have to put a, you know, a bracket. So let us run this now. Right, so we'll let it run. Okay, it has finished. It is it has already finished, but it has done quite a good job. So you can see here that it has, worked perfectly fine in case of damage reduction, right? So after every epoch, we have gotten the losses as well, right? And this is after epoch number 15. So we are not getting, we are not getting any substantial reduction in the losses after a certain point, right? Or it's the same thing maybe. Let us see what is going on here. Uh, let me check this out because there has to be some issue here because we are only using the encoder only, right? So that's completely fine. But the problem is this has to be outside of the for loop. And that is why I'm getting this. And if you run that one more time, lastly, there you go. So now we are getting a decrement in losses, or are we? No, we are not. Oh, we are, right? 0.19, then 0.08, and that's it. There's not much of decrease after a certain point. How about this one then? Just a second. Okay, let us do this. Put this in the same cell as this one. I don't think it will matter that much, but let us put that in the same cell here as this. Right. Let us run everything. Yeah. So it's working fine. You can see here that we are able to, reduce the dimension of our data from, 3 to 2. Okay. So we are going to be using autoencoders on image data to denoise the images. How we are going to do that is I'll use a famous dataset, that is MNIST dataset, and I'll put some noise first and then we'll kind of denoising it. So I'll quickly import some of the libraries. I'll say import pandas as PD. I'll import NumPy. I'll import matplotlib, that is the visualization library, as PLT. And I'll also say from TensorFlow dot keras dot datasets import MNIST dataset. Okay, I've got a indentation error. Just remove that space and run this one more time. Now, why we are using TensorFlow here? This is just to get the data. That is, if I say MNIST dot load data, you can take NIST dataset from anywhere else as well. If you are aware of that, again I'm using TensorFlow just to get the data, and if you run that, you will get bunch of things here. The way it is organized is you have two tuples, that is in two tuples you have, or should I say a tuple of tuple. So one tuple is about the training set, so this is x train comma y train, and the next tuple is x test comma y. So I'll say plt dot show, for example, take x train just to visualize the image, and just take any index. For example, you can take the index number 10 and you run that. I'll get an error because this is plt.imshow. Okay, so you can see you are getting this kind of, this image here, right? And you can just pass in any other index number. For example, you can pass in 100 and that is going to give you image at that particular index. You can also get the label here, for example, as well. So if I say y train here and pass in that particular, index number, that is 100, I believe. So this is number 5 apparently. It doesn't look like 5, but it doesn't matter. But you can put any other number again to perhaps this surely is 7. So if I run that, the label, yeah, it is 7. Okay, so you can see I have gotten X train, Y train, and X test as Y test. Similarly, you can put here, X test as well to just display the images. Again, display of the images and all that we have already taken care of that in our other uh, sessions. For now, I'll start with normalizing the images. So X train equal to X train divided by 255. I'll say X test equal to X test divided by 255. All right. Then I'll say basic auto encoder. All right. So I'll say import torch dot, well, never mind. From torch import nn. Okay. And I'll say from torch dot utils dot data import data loader to load the images in batches. Then from torch vision, although it is not needed, but still I'll have to import the transforms, and I'll import also the data sets. So this is importing the Torch library, which provides the support for tensor computation and automatic differentiation in tensors. And this one, it is importing the module, that is NN module from PyTorch, which provides the classes for building neural network. Then we are importing the data loader, which is used to load the data in batches, shuffle the data, parallelize the parallelize the process, and then we are also importing the transform, that is, going to transform the data set as per our requirement. So that allows for data pre-processing and augmentation. What I'm going to do also is I'll set the device here. So you can say device is equal to torch.device. Again, if you're using CUDA, you can do that over here if available. So torch dot CUDA dot is available, else let's say CPU. It defines the device on which the computation will be performed. So if a GPU with CUDA support is available, it will use CUDA. Otherwise, it will default to the CPU. Uh, Also, I'll load the MNIST dataset. So the way we are going to be doing this is this. I'll say train data is equal to data sets dot MNIST. I'll say root equal to dot forward slash data and train equal to true. Also, I'll put download equal to true. So again, I'm using PyTorch MNIST dataset instead of this. So this is good for displaying purpose, but I'm using PyTorch dataset only, right? So that, it becomes rather in line with everything that we are doing. So download equal to true. And one more thing is transform equal to just transform it simply, because all the images in this particular dataset, they are with the same shape, that is the same height then and same width and all that. So it is 28 by 28 images, so we don't have to actually do anything. And also they are on same scale as well, that is the pixel values from 0 to 255. So you don't have to worry about that in this case, but if you want, you can normalize that as well separately if you want. But I'll similarly put test data as well. This is train equal to false. Let us create data loaders. I'll say train loader equal to data loader. Pass in the train data, comma, batch size equal to, I'll put a batch size of 32, and I'll shuffle equal to true. Now you can take any other batch size as well. Instead of 32, maybe you can take 10 or 64, whatever. But there's 60,000 images. So batch size 32 is going to maximize the, memory here. But I'll say test loader here equal to data loader again. And in this case, we don't have to shuffle anything. And also I'll use the test data and batch size equal to 32 and shuffle equal to false. So it creates a data loader for training data with a batch size of 32, and data is shuffled at every epoch to ensure that the model does not learn the order of the data. then we are creating the data loader for the test data with the batch size of 32 again. But in this case, data shuffling is not required since the order of the test data does not matter when you're evaluating it. That is evaluating the model. Once this is done, then we are going to define the class autoencoder, and it is going to inherit everything from nn.module. I'll say def underscore underscore init underscore underscore and super. I'll say auto encoder comma self dot underscore underscore init underscore underscore as is. Right. So it defines a autoencoder class which inherits from nn.module. That is the base class for all the neural network modules in PyTorch. Then we are creating this def underscore underscore init underscore underscore self. That is a constructor method for the class which initializes the model's layer. Then the super, it calls the constructor of the parent class, that is nn.module. Then I'll say self. So I'm creating a sequential container for the encoder part of the autoencoder that is going to stack up the layer one after another. So I'll say self.encoder equal to nn.sequential, and here this is nn.flatten. So it flattens the input image. Again, it flattens the input tensor starting from the first dimension, which converts the 28 by 28 image into 784 element vector. So if you multiply 28 into 28, you are going to get 784. So we are flattening out the image input, and then I'm saying nn.linear is going to take 784 obviously at the input layer. So this is the number of neurons that you have to have. So a fully connected layer with 784 input feature and hopefully 400 output feature. Then I'll say nn dot relu. I'll say in place is equal to then nn dot linear 400 to 200. Then nn dot relu is going to take in place equal to, then I'll go from 200 to 100 and then dot linear 200 to 100 and then dot relu in place equal to true, and then dot linear. Lastly, I'm going from 100 to 50 and maybe I'll just take one more, right? So 50, then and then dot relu again in place equal to true, because 50 is not enough. I'll have to again further tone down. So I'll go from 50 to 20 and also nn dot relu in place equal to true. Again, what we have done here is we have defined the encoder part of the autoencoder that stacks the layer. All these layers, we are stacking them all one after another. And then we have here flattened out the image that is converting from 28 by 28 image into a 784 element vector. Then a fully connected layer with 784 input features and 400 output feature. Then it applies the ReLU activation function to introduce the nonlinearity. In place equal to true, it modifies the input directly without allocating any new memory. Then we are going from similarly from 200 to 100, then 100 to 50, then 50 to 20. That's how it's going to work. Then I'll say here self dot decoder equal to nn dot sequential. Here I'll say nn dot linear, pass in 25 to 50, nn dot relu here is in place equal to, and nn dot linear is going to be 50 by 100. So the way I'm doing this is I'm going now in opposite direction. Sorry, it is 25. Is that so? Okay, let us put 25 here. So we are going from 25, and in decoder pi, I'm going back to 25 to 50, 50 to 100. Then I'll go from 100 to 200, 200 to 400, 400 to 784. That is how the encoder is being made. or that is the architecture of the autoencoders. So 100 and then again relu in place equal to true, comma. And what I'll do is, I'll just copy this thing so that I can just paste it again and again instead of typing this. So I'll say nn dot linear here is we are going from 100 to 200. nn dot linear, I'm going from 200 to 400, and then nn dot linear, I'm going from 400 to 784. And then lastly, when you get the output, obviously I'll have to put a sigmoid function. This cannot be relu function. Also unflatten it. nn dot unflatten is going from one color channel to 1 into 28 by 28. Okay, let me show you, explain this one more time what I have done. So basically, now we have defined the decoder part. We have created the sequential container again for the decoder part, and where we are going from 25 to 784. Okay, again, it is just like opposite of what we have done in the encoder part. And lastly, we have used sigmoid function that is at the output layer, which scales the output value to a range between 0 and 1 that is suitable for grayscale image pixel. And then I'm reshaping the 784 element output vector back to the original 28 by 28 image format that we had in the first hand. Now I'll take this and say def forward. So I'll have to define the forward pass as going to say self comma x encoded equal to self dot encoder and decoded equal to self dot decoder. Sorry, in this case we have to pass in the encoded, and lastly I'll return the decoded part. So again I'm using both the things here. Let me run this one final time, and after that I'll create the model instance. So once you have defined this model, let me create the instance of this model here. I'll say model or autoencoder model, doesn't matter. You say auto encoder dot to then the device that we are using. By the way, the device that we are using as of now, I think it is CPU, unless I have changed this to GPU. Yeah, it is CPU. Again, CPU is going to be very, very, slow, and that is why we'll have to use the GPU. Now what we have to do is we have to create the criterion here. I'll say criterion equal to nn dot bce loss. Great. And this is again binary cross entropy loss for image construction, and it's binary cross entropy because the autoencoder does not really care how many distinct type of number there are. So it does not really care that there are 10 classes for the number. All the autoencoder cares about is the image that I'm producing at the output is going to match the image that was originally put into the input. So that is why it's just a sigmoid and the binary cross entropy. So I'll say optimizer equal to torch.optim.sgd, pass in the model dot parameters, and learning rate, you can put any learning rate here. I will just put 0.01, and then I'll train the model. Number of epochs is obviously something that I'll have to define. I'll put simply as 10 in this case, and I'll say that for every epoch in range number of epoch, here you have to do following. For every I comma images underscore in enumerate train loader, I'll get the images to device, because if it is on CPU, then you'll have to put that to GPU. So if you are using the GPU, then I'll have to transfer that. So I'll take those images and say to the device. All right. Then I'll make it through the forward pass, that is outputs equal to model, and set that we have the images. I'll say loss equal to criterion. You have to pass in two things. One is the one that you have predicted, that is the outputs, and the images themselves to calculate the losses. And then the back propagation step, that is the usual one, that is the optimizer zero grad, and loss dot backward, then optimizer dot step, and I'll say if I plus 1. Why I plus 1? Because I want to, print the result after every, for example, 100 epoch. Sorry, after every 100 batch. So I'll say I plus 1 percent 100. Whenever this is 0, I'll say print f literal epoch, and that is going to be epoch plus 1 divided by number of epochs, and that's going to be this. I'll say step here. This is going to be I plus 1 divided by length of train loader, and this has to be inside the curly braces as well. Okay, then I'll also get the losses. For that, I'll put here, I'll say loss dot step here, not step, rather loss dot item, this to be 0.4f. Okay, then I'll say that with torch.nograd, I want to get the test images. So this context manager tells PyTorch not to compute for store gradient, basically, that is with dot no grad. So since we are testing the model, not training it, we don't need to, we don't have to have the gradients, which saves the memory and computation. So I'll say next test images rather is equal to next iteration of the test loader and 0.2 and device. All right, and say reconstructed equal to model and test images. Okay, so again, what we are doing here is we are retrieving the first batch of the data from the test loader. Then this 0 basically selects only the image from the batch and ignores the label. Then this two dot device, obviously it is going to move to the specific device, whether it's a GPU or CPU, whatever you have chosen. Then reconstructed images means it passes the test images through the autoencoder model. The model generates the reconstructed images, which are the output of the decoder after the images. After the images have been basically encoded and decoded. Then what I'm going to do is I'm going to basically plot the reconstructed image. Let me show you how to do that. So this is for visualization. Visualize the just any just first reconstructed image. You can take any other image here, right? So I'll say that plt.imshow, I'll say reconstructed images 0 dot cpu dot squeeze cmap, color map is grayscale, and I'll say plt.show as well. Run that. Yeah, there has to be a parenthesis here. And once you have this parenthesis, there's no need for this one, I think. Let us run that. Okay, I got again some error. It is missing the forward function. Is that the case? I don't think so. Oh, I see. So the problem is with the indentation. You have to put that over here. And similarly, there you go. Right. Now you can run that once more. And again, encoded is not defined. Where is it? There's some spelling mistake. You can see there's a spelling mistake here. I'll have to go back and fix that. This is over here. So just remove this O, extra O, and run this one more time. Great. Now it is working fine. Now what I'm going to do here, obviously, is going to take significant amount of time. I'll stop this and turn on the GPU. How are you going to turn on the GPU? I'll go to change runtime in this runtime option. Go to change runtime and just click here and save it. Once you save it, you can see it is allocating runtime on your on its GPU. So let it let it finish that. Now run everything.